Something impossible showed up in a simple backyard telescope, a raw frame, no fancy processing, no institutional logo, just a sun watcher pointed exactly where the official trackers said 3i Atlas should be. The picture lands and the rules of comets stumble. A bright jet points toward the sun instead of away. The core looks hard and dark in the imaging mode. The usual glowing shroud is barely there, and the tail you expect to see is missing. If this grabs you, like and subscribe now, so you do not miss what comes next. Here is the scene. A private observer aims a solar telescope at the coordinates released for 3i Atlas and captures a clean frame near the sun's blinding neighborhood. Solar telescopes are built for this job. They are tuned to do the hard things safely. You will see colored speckles from the camera sensor and the jitter you expect in hot air, but the core signal is stubborn. A narrow feature leans straight at the sun, not away, not curling along a gentle arc. At the center, the brightness inverts as expected for this imaging style and leaves a compact dark spot where the nucleus should be. Around it, almost nothing. That near nothing is the problem. Real comets behave like kettles on a high burner. Sunlight hits, ices skip the liquid step and turn into gas. Dust rides that gas into a fuzzy envelope called the coma. Radiation pressure and the solar winds shove that material away from the sun. The result is a tail you can sketch with a crayon. One stream of dust that bends along the path. One spear of ions that points straight away like hair in a hard wind. It is reliable. It is repeatable. It is why every child's comet drawing looks the same. So what if this is not a camera trick? What if a forward jet is real? A localized outflow can happen on an active patch of surface, but the rest of the comet should still be huffing and shedding dust into a broad glow. In this frame, the broad glow barely exists. You can squint and find a faint cone drifting off to one side, small and contained. The rest is clean space. If the coma were robust, it would flood the sensor with scattered light like fog around a street lamp. Even a modest instrument would see that halo. It is not there. Could the optics fake a structure? Diffraction spikes tend to be symmetric and cling to bright points. Blooming smears along sensor columns. Random hot pixels scatter without shape. Atmospheric soup blurs edges evenly. None of those behaviors pick a direction that points back at the sun and holds steady across the frame. The simplest reading is the one in front of us. A signal sits where a signal should sit, and it points the wrong way. Could timing rescue the standard script? Comets do pulse. As a nucleus turns, active vents swing in and out of sunlight. Output can surge or stall, yet this object is days from closest approach to the sun. That is usually prime time for a dramatic increase in gas and dust. The slow simmer becomes a rolling boil. If 3i Atlas is natural, this is when it should look the most comet-like. The frame shows the opposite mood. Maybe geometry is playing tricks. There is a known effect called an anti-tail that can make dust seem to point sunward when we view the orbital plane edge-on. That can fool the eye. It does not erase the coma. An anti-tail rides on top of a larger, softer cloud of material. The image here does not carry that cloud with any conviction. The organized line exists. The diffuse envelope does not. The mismatch keeps nagging. The source matters. This was not a secret lab. It was a careful hobbyist who knows how to work near the sun, who posted a raw frame at a specific universal time, and who explained the settings in plain language. RAW is valuable because it removes one layer of doubt. No stacking choices, no curve tweaks, no sharpening halos to confuse edges. Photons hit a detector and got recorded. When a simple pipeline leaves you with a forward jet and a quiet background, you sit up. There is also the clock. 3i Atlas is sliding behind the sun from our point of view. Earth cannot stare through that glare. For a brief stretch, the perfect place to act is also the one place we cannot watch. That is not drama for its own sake. It is orbital geometry. It turns the picture you just saw into a before shot. What comes next will be known by what comes after. If it is a comet, tails should blossom once it swings back into view. If it is a machine, shape and attitude may hold steady, and other objects may peel away. So the paradox sits on the table. Physics says a tail is not optional. The image says the tail is not obvious. One of those has to bend. Our job is not to force a conclusion. Our job is to test stories against the sky. We will walk through what comets should do, what illusions can fake, what spectra already hint, and why the timing around closest approach is the most efficient moment for any planned maneuver. Then we wait for the next frame. A last note on trust. Science is not a vibe, it is a process. You start with something anyone can point a camera at. You explain what you expect to see. You highlight what fails to appear. You ask whether known quirks can mimic the weird thing. If they cannot, you keep the weird thing on the board and you invite more eyes. That is how a backyard photo becomes the first chapter in a serious investigation. The sky does not owe us simplicity. Sometimes it hands us a clean paradox instead. A sunward jet, a quiet coma, a missing tail, 8 days to heat and speed at their peak. Hold that picture. We will try to break it. If it survives the stress, the story changes. If it crumbles, we learn and move on. Either way, the next pages write themselves when the object comes out from behind the light. Before we chase the mystery, we build the baseline. A comet is an ancient mix of ices and dust. Far from the sun it sleeps. As it falls inward, sunlight wakes it. The surface warms and the ices skip, like the liquid phase, and turns straight into gas. That step is called sublimation, and it drags grains of dust into space like a crowd carried along by a subway surge. Around the nucleus, a fuzzy atmosphere forms. Astronomers call it the coma. If you have ever seen fog in a car's headlights, you already know what a coma should look like. Now the tails. Comets often wear two at once. The dust tail is the painterly one. It curves gently along the orbit because dust has inertia, and sunlight nudges it rather than flinging it. The ion tail is the arrow. The solar wind, a river of charged particles that flows outward from the sun, grabs ionized gas and pulls it straight away. That is why comet drawings from children on every continent share the same geometry. Soft curve for dust, sharp line for ions, both point away from the sun, never toward it. This machinery is not guesswork. We have watched it for centuries through small eyepieces and giant mirrors. We have flown spacecraft to comets. We have landed on them and listened to grains ping, instruments like tiny hail. Over and over, the same pattern repeats. Move inward and brighten. Grow a fat coma. Grow 1 or 2 tails. Align those tails away from the sun. Then, sometimes, crack under the strain. Natural behavior can be dramatic, but it is reliably dramatic. There is a rhythm to the brightening as distance shrinks. Think of a campfire. Step closer and you feel heat climb fast, not gently. The same acceleration happens to a comet. More sunlight becomes much more heating. More heating becomes much more gas. The coma thickens and scatters even more light. That feedback is why comets often surge in visibility near closest approach. If you could plot brightness against distance, the curve would sweep upward like a hill that suddenly steepens. Jets fit within the script too. A nucleus is not smooth. It is a lumpy worldlet with cliffs, pits and crust. Sunlight strikes one patch more than another. A crack opens. Gas channels, outward like steam from a kettle spout. You can see thin fans and plumes in high-resolution images. Those localized outflows spin with the body's rotation and contribute to the larger haze. They are the soloists in a choir. Loud for a moment, but the chorus is the coma itself. The coma matters for another reason. It is forgiving to instruments. Even a small telescope that cannot resolve the nucleus can still detect the light sprinkled across a wide halo. Imagine photographing a streetlight through light mist. You might not see the bulb sharply, but you cannot miss the glow. That is why absence of a convincing coma near the sun feels wrong in the gut. The easiest part to see has gone shy. Geometry can play tricks. When Earth passes through the plane of a comet's dust, the long trail along the orbit can look like it points toward the sun. Astronomers call that an anti-tail. It is a viewpoint illusion, not a reversal of physics. Even when an anti-tail appears, the broader coma still wraps the nucleus. If you see a neat sunward feature without the surrounding glow, you should pause and ask what else could mimic that view. We also know what a natural slowdown looks like. Comets can have quiet spells. If a crust quilts over active regions, outgassing can stall until fresh surface is exposed, but a stall right before closest approach would be odd. This is when the thermal wave digs deepest and shakes loose material that has slept for ages. Short dips can happen. Long silences near peak energy are not the norm. All of this leads to a simple test. When the object rounds the sun and returns to darker skies, a true comet should reward every backyard observer with classic features. The coma should billow, the dust tail should sweep, the ion tail should spear away, brightness should rise and then fade along a predictable path. If those signatures arrive on schedule, we chalk up the earlier weirdness to angle, timing, or limits of the first images. Case mostly closed. If those signatures do not arrive, the baseline breaks. The physics lesson you just heard does not vanish, but its relevance to this object drops. That is why we built the model carefully and in everyday words. It is not to lecture. It is to give you a ruler. With a ruler in hand, the the next frames will be easier to judge. Do they measure like a comet, or do they refuse the measurement? We do not need equations to hold this picture steady. Sunlight in, gas out, coma glows, tails point away. Near the sun, everything gets louder. That is the loop. The fact that it repeats across countless visitors is what makes the outlier so gripping. If the next appearance of 3i Atlas breaks the loop again, the story moves from odd comet to something stranger. If it falls back into line, the universe just taught us humility. Either way, the baseline has done its job. Start with a person, not a lab, a hobbyist who understands the sun's neighborhood and treats safety like religion. On October 20th, they point a solar telescope to the published coordinates for 3i Atlas. Hold the exposure short to protect the sensor, and let the photons do the talking. A single frame is posted at a specific universal time, with a simple caption. Raw, no curves, no sharpening, no drama. The image hits the feed and 1,000 eyes blink. A narrow feature points straight toward the sun. The core sits like a hard seed. The expected glow around it is a whisper. Why should you trust an image like that? Because solar telescopes exist for exactly this problem. They are tuned to the bright soup around the sun where ordinary instruments wash out. Narrowband filters cut most of the glare and let you see structures that live in the near-solar sky. The coloured specks scattered across the frame are familiar to anyone who has ever wrestled a camera sensor. Hot pixels. Cold pixels. They sit where they want. They do not line up to form an arrow that anchors at the object and leans toward the sun. Noise has a look, so do artifacts. Diffraction ornaments hug bright points and echo the shape of a telescope's support vanes. Electronic blooming bleeds along neat sensor columns. Cosmic ray hits leave tiny scratches or dots that repeat nowhere else. Seeing blur from hot daytime air shakes every edge equally and robs contrast. None of those tricks are picky enough to draw a clean sunward line tied to the darkest knot in the field. The structure here behaves like signal. It anchors, it keeps its direction. It remains visible when you invert the palette to emphasize contrast. It is not a smear carried by a row of pixels, it is a feature. Raw matters. Processed images can be honest, but they always carry choices. How much to stretch the shadows, how hard to sharpen, whether to align and combine many frames to beat down random noise. Those choices can lift faint detail and can also manufacture ghosts. A raw frame is blunt. What you see is what the detector saw. If a tail is there, it is usually the easiest thing to spot because it spreads light across many pixels and behaves like fog in a headlight beam. If the raw frame shows a narrow jet with almost no surrounding haze, you do not get to blame the software. The observer also tells us their plan. They will switch to a normal night telescope after closest approach when the object exits the sun's glare and climbs back into dark sky. That line matters. It reveals someone who knows the gear and the geometry. You use the solar rig when the sun owns the scene. You use a night rig when the sky goes black again. It also telegraphs confidence. They expect to see the object again and are ready to test whether a classic tail finally appears when conditions favour it. Why would an amateur see this first? Because professional observatories have strict keep-out zones near the sun to protect optics and sensors. Because scheduling is tight and daylight hours are not built for comet work. Because the most motivated instrument is the one in a backyard when a person decides to try. Citizen science is not a consolation prize. It is a sensor network spread across the planet with no committee and no red tape. When a solar-trained amateur shares a clean frame and the geometry matches the ephemeris, you take it seriously. Could there be a boring explanation? Always ask that. Maybe the sunward feature is an anti-tail, a dust sheet seen edge-on that tricks the eye into reading toward the sun. The effect is real. Yet an anti-tail normally rides on a big bright coma. The sheet is not a needle. It is a slab of dust embedded in a much larger halo. Here the larger halo is faint and tightly contained. The line reads like a focused outflow, not a wide road of dust along the orbit plane. What about timing? A comet's breath can stutter. Rotation turns vents in and out of heat and can swing a jet in odd directions. Even so, the weeks before closest approach are when the kettle should scream. If you are going to see the classic look, this is prime time. The lack of a broad coma is the part that refuses to fade with a shrug. You can wave away a missing tail for a moment. You cannot wave away the silence of the easiest feature to detect. The credibility test does not end here. It begins here. Others can point similar gear and check the scene the way birders confirm a rare sighting. If a second and third solar telescope catch the same sharp sunward structure with the same subdued coma, confidence climbs. If only one rig ever sees it, confidence falls. That is the beauty of a claim that lives or dies on the sky. Anyone with the right filter and safe habits can try, so the frame becomes a marker. The last clear view before the object slips behind the sun from our perspective. The forward jet, the quiet surroundings, the missing textbook tale. A citizen scientist forced the opening move by putting raw light on the board. It broke the silence not by shouting, but by leaving out the thing everyone expected to hear. We will either see the chorus return when the object emerges, or we will listen to the soloist again and admit the song is different. If a backyard telescope can pull a clean frame, where are the giants? Where are the observatories with mirrors big enough to catch starlight in their hands? The question is fair. It is also tangled with safety rules, geometry, and the quiet bureaucracy of space science. Big glass and billion-dollar spacecraft do not wander near the sun's glare on a whim. They live by keep-out angles and survival checklists. A small mistake near the sun can cook a detector or blind a star tracker. That is not drama. That is heat. Start with geometry. When an object sits almost behind the sun from Earth, the line of sight runs through a wall of scattered daylight. The sky itself becomes a bright screen. Ground telescopes fight atmospheric glare, boiling daylight air, and safety shutters that lock when the sun is too close to the field. Twilight windows help sometimes, but only when the object's angle from the sun opens enough to sneak a look. During conjunction, the angle shrinks until the only honest answer is no. Space telescopes have their own limits. One protects itself with a giant sunshade and must always keep that shield between its mirrors and the star that warms us. Another avoids direct sunlight by strict orientation rules. Pointing anywhere near the sun is either forbidden or so tightly constrained that the right target can live just outside what is allowed. You can fly a ballet of slews around those rules, but you cannot break them. The machines survive by caution. Solar observatories are built for brightness yet still have blind spots. A coronagraph can cover the sun with an artificial eclipse and reveal the ghostly corona, but faint point sources close to the occulted disk are tricky. The algorithms that hunt for sun-grazing fragments are tuned for fast flashes of light against swirling solar structure. A slow, not very bright, interstellar object can slip through that net unless it crosses the right sweet spot at the right time. Even then, the cadence and compression can make a marginal target look like background. Then there is the human side. Big observatories run on schedules set weeks or months in advance. Priority targets claim their nights long before a surprise visitor crowds the inner system. Daylight is not a friend for most ground instruments. Solar-trained facilities book their time around space weather, not deep sky interlopers. Managers weigh risk. Is a near-sun target worth shaking up the calendar? If the sun angle is tight or the safety margin slim, the answer often lands on not this time. Even when a spacecraft can take a peek, pipelines add delay. Raw packets do not leap to the public in real time. They queue for downlink windows, run through calibration software, get flagged for quality issues, and sometimes wait for teams to confirm that what looks like a feature is not a processing ghost. That lag can be hours or days. To a hungry public, delay feels like silence. To an operations team, delay is prudence. Absence invites a second kind of noise. When big instruments go quiet, rumor grows fast. Some outages are mundane. Star trackers trip and put a craft in safe mode. Ground stations switch antennas. Software gets patched. Other gaps are simple geometry. If the target is behind the sun for us, it can be behind the sun for a satellite near us as well. The result is the same on a social feed. Empty days look like a hush. The mind fills the gap with whatever story fits its mood. None of this negates the power of small telescopes. Citizen science thrives where institutions cannot or will not move quickly. A backyard rig can nudge close to the sun under careful filters and post a raw frame without waiting for a committee. That agility is not a threat to big science. It is a complement. One finds the odd thing. The other weighs it under better conditions, when the geometry softens and the safety lines loosen their grip. There is also a path to better coordination. Publish clear windows when professional assets expect to see the object again. Share simple checklists for solar-trained amateurs so that repeated attempts rhyme. Invite duplication on the same day so that artifacts die quickly. The fastest way to drain rumor is to flood the zone with methods anyone can try. When a map of who can look and when sits in public view, silence stops feeling like secrecy and starts reading like weather. So where are the big telescopes? Waiting for angles to open, protecting hardware that must last years, choosing not to gamble a flagship on a risky sunward shot. Quiet does not prove a cover. It proves the machines we love are mortal and their keepers careful. In the meantime, the smallest lenses on Earth have stolen a march. They gave us the last clean look before the blind window. When the object rounds the sun and slips back into night, the giants will speak. If the coma blossoms, they will show it. If the shape holds and companions appear, they will show that too. The next word belongs to the sky, and the big mirrors will carry it. So what if the tail is not pointing away at all? What if geometry is playing a card that looks like defiance? Anti-tails are real. When Earth lines up close to the orbital plane of a dusty comet, the long sheet of particles that trails along the orbit can collapse into a thin, bright spike that appears to point toward the sun. Your eyes see a spear. Physics still pushes dust away. Perspective flips the picture. Picture a paper ribbon taped to a fan. Viewed from above, it flutters back. Viewed edge on it can look like a straight line pointing the wrong way. That is an anti-tail in plain language. It is a trick of alignment, not a reversal of the forces that make comets behave. Astronomers have watched this illusion before. Each time, the larger scene still gave itself away. A wide, glowing coma wrapped the nucleus. The dust sheet blended into that glow. Nothing about an anti-tail deletes the fog. It only arranges it in a neat line for a while. Now look back at the solar frame that sparked this. The narrow feature is present. The broad fog is not convincing. You can whisper the shape of a small puff off to one side, yes. You cannot claim the generous halo that should flood the sensor if dust and gas fill the space around the nucleus. This mismatch is the grit in the gears. Anti-tail explains direction. It does not explain the near absence of the very thing that makes comets easy to see. Could a single jet masquerade as an anti-tail? A hot vent on the surface could shoot gas and dust in a tight stream. If the spin axis and the sunlight line up just so, that stream could aim roughly sunward. Jets happen. We have photographed them on multiple visitors. They twist as the body turns, and they build the larger coma as particles spread and collide. A lone jet that stays thin and organized while the background stays quiet right before closest approach would be unusual. Not impossible, unusual. There is another possibility that feels less like geology and more like engineering. A sunward face that is different by design. Imagine a thermal shield that wears the heat, bright on the side that faces the star and dark elsewhere. The Parker-style idea in human terms works the same way. Keep one side tough and hot. Keep the rest cool and protected. If an object held a stable attitude with that side toward the sun, you would expect two things: a consistent geometry that resists tumbling, a brightness pattern that refuses to smear into a fog even as heating climbs. That is not proof, it is a tell to watch for. Phase angle can help us think this through. When the line from sun to object to Earth changes, the way light scatters off dust changes too. True dust clouds brighten in predictable ways as the angle shifts. Glint off large particles, forward scatter that boosts the sun, facing arc. If the narrow feature simply rides on dust, its brightness should rise and fall with that dance. If it is a hard surface or a plasma sheath near a surface, the changes could be very different. That is a test we can run as the geometry opens in November. Polarization is another tool. Light scattered by dust grains is polarized in characteristic patterns. Smooth, solid surfaces polarize light differently. Even modest instruments with polarizing filters can probe that difference. If many observers measure a polarization signature that fits a thin dust sheet, the anti-tail case grows stronger. If the signature looks like reflection from a hard face or emission from excited gas without the usual dust pattern, the shield idea gets a push. Rotation should leave footprints as well. Jets tied to spinning terrain sweep across the sky over hours and days. The line they draw should wobble or fan slightly. A shielded face on a stabilized craft should hold its aim. If the sunward feature refuses to drift while stars crawl through the background, attitude control belongs on the suspect list. Even a very slow natural spin ought to smear a vent line a little over time. Sharp and stubborn is not the natural style. What about a bow shock in the solar wind? A moving body can pile up charged particles on its sunward side. That pile can glow. Could a plasma sheath create the narrow feature without big dust participation? Possibly for a while. Yet even then, near closest approach, the heating should blast volatiles into a coma that rides along with any sheath. A plasma trick explains a rim of light. It does not pay the bill for an entire missing fog. Let us lay out the clean discriminators that the next frames can deliver. If it is an anti-tail, the line should evolve as our viewing angle changes. It may flip from neat to messy as we move out of the orbital plane. The general coma should reassert itself in darker skies. If it is a forward jet, short-term oscillations should appear as the nucleus turns. The background haze should grow louder as heating peaks. If it is a sunward shield or another engineered surface, the orientation should stick, the line should stay crisp, and secondary objects may appear to separate along planned paths rather than drift as debris. None of this demands instant judgment. It demands patient watching with a clear mental checklist. Direction alone never proves intent. Direction without the usual company of a fat coma is why we pause. Geometry can fool your eyes. It cannot forever fool a timeline filled with new angles, new filters, and many repeat observers who share raw files. That is how an anti-tale reveals itself as a trick or a clue. So we stand on a narrow ridge between two stories, a comet sheet seen just so, with our line of sight slicing the dust plane into a spear, or a sunward face that behaves like a purpose-built shield. The ridge will not hold for long. As the object rounds the sun, the angle changes and the data stream grows. The next time you see that narrow line, ask whether the fog finally showed up to surround it. If it does, the ribbon on the fan wins. If it does not, the face in the fire remains. Then another video landed and the room went quiet. Not near the solar glare this time. Deep sky. A dark field with steady stars and a single object that refused to behave. Long, smooth. Bright along its length, no fuzzy halo, no broom of dust, no spear of ions, just a form that looks like a rule breaker and feels like a dare. If the first photo poked the bear, this clip grabbed it by the collar. Start with what the eye can measure without a ruler. The object stretches many times longer than it is wide. Think of a pencil held at arm's length, not a potato in space. The brightness along that length is strangely even. Natural rocks lit by the sun tend to glitter and fade as facets turn. Here the light does not pulse or flicker in a way that screams rough terrain. It reads like emission, more than reflection, as if the object is glowing from itself rather than just throwing sunlight back at us. Now look at motion. Stars hold steady in the background. The object drifts across the frame without the jitter and smear that betray an untracked camera. If the telescope tracked the stars, a fast object would streak. If it tracked the object, stars would blur. Here, star points look honest, and the target remains a coherent shape. That coherence matters. It means we are not just squinting at a lucky blur, we are seeing a thing. What would a natural nucleus look like at this stage? A lumpy chunk wrapped in gas, brightness concentrated near the center where the coma is thickest, a fuzzy edge that breathes with rotation, and a tail that, even if faint, remembers where the sun is and points away. This clip refuses all of that. The edge is too defined. The core does not sit inside a flattering halo. The tail is absent as a concept. You can try to read a soft smear into one side if you want to be generous. The frame does not reward generosity. Could angle explain the long shape? Sure. A thin shard oriented just so could appear stretched. We have seen elongated natural bodies. The famous visitor years ago likely had a wild aspect ratio, but most elongated rocks tumble, and that tumble writes its signature in changing brightness and orientation. Here, the long axis stays committed. The brightness stays steady. The overall pose feels deliberate. Maybe the rotation is slow. Maybe we caught it near a pole, or maybe it is holding attitude on purpose. What about digital ghosts? Diffraction ornaments? Column bleed? Compression blocks? Each has a personality. Spikes are symmetric and center-on-point sources. Bleed marches along neat rows. Compression makes chunky squares. The deep sky clip does not act like those. It acts like a bright, extended source that is drawn with a single hand. Even the ends taper in a way that looks engineered, not ragged, as if the structure has an intended length and stops there. There is a human reaction that matters here. Pattern recognition is not a sin. It is how we cross streets and solve puzzles. When many people look at a shape and whisper craft under their breath, it is not proof, but it is a data point about how, unlike a comet, this looks. The word mothership came up because linear forms with even light feel like trusses, hulls, and radiators, not like ice and dust. That feeling should not run the investigation. It should push us to ask better questions. So ask the right ones. Does the brightness change with phase angle the way dust clouds do? Or does it behave like a hard surface or a controlled emission? Does the shape evolve as viewing geometry shifts? Or does it hold profile as if stabilized? Can independent observers replicate the length-to-width ratio and the lack of coma with different optics and cameras? Do any spectral hints appear in concurrent data that match metals or engineered materials rather than common comet gases? There are natural outs, and we will give them air. A narrow jet could align with our sightline and mimic a rod. A thin debris sheet could brighten just right when we look along its plane. A slow rotation could hide itself over the seconds captured in the clip. Each of these would still have to survive the next round of footage when time and angle move on. Illusions are fragile across many viewpoints. Machines are not. Also remember the context you already carry. We have a solar frame with a sunward line and a quiet coma. Now we have a deep space clip with a stretched, even brightness form and the same coma problem. Different gear, different conditions. Similar defiance of the textbook. Coincidence can happen twice. It can. But the mind is allowed to raise an eyebrow when two unrelated cameras rhyme on the same theme. What would seal this chapter? A repeat capture with polarizing filters that show dust scatter, which would pull us back toward geology. Or a light curve, across minutes that shows a telltale tumble, which would soothe the nerves of anyone spooked by straight lines in space. Or, on the other side, a set of frames that show a fixed attitude through changing geometry, plus a stable edge profile, plus a brightness that does not care about sun angle in the way dust does. That combination would make the technological reading very hard to ignore. Until then, we sit with the picture that changed the mood. A long glow on a black canvas, no drama around it. No wild shed of material, just a shape that looks like a decision and moves like one. If this is nature, it will soon betray its tricks as the angles change and the heating rises. If it is not, the next clips may start to show companies separating from the parent, points of light peeling off along thoughtful paths. Either way, this was the moment when many viewers stopped saying weird comet and started saying something else. Before we jump to the wild conclusion, we try our best to break the evidence. That is how real investigations work. First you ask how the picture could be lying, then you try to make it lie on command. If the tricks fail, what remains is worth your full attention. Start with the usual suspects in optics. Diffraction spikes are the Christmas ornaments of bright points. They mirror the shape of the telescope's support vanes and radiate symmetrically from the star that caused them. They do not anchor on a dim knot and draw a single arrow that points at the sun. Blooming is an electronic overflow. Charge spills down neat columns of pixels and makes tidy vertical or horizontal streaks. It does not lock to a moving target and hold a steady diagonal line. Cosmic rays hit the detector like tiny bullets. They make razor-thin scratches or sharp dots that appear in one frame and vanish in the next. They do not cling to a nucleus through multiple frames or across independent cameras. Atmosphere plays its own tricks. Hot daylight air wobbles an image, softening edges and bending shapes across the field. That flutter does not pick a favorite direction for long. It blurs everything a little and makes stars twinkle. It does not erase a wide coma while leaving a thin, sunward feature crisp. Thin cloud can add grain and milk the contrast, yet it milks all of it. If a structure keeps its shape while the background swims, suspect the structure less and the swim more. Processing is the quiet saboteur. Stretch the histogram too hard and you build halos. Sharpen aggressively and you draw false edges. Stack many frames and you can smear moving features if your alignment is off by a hair. The cure here is simple. Post the raw frames and let others process them their own way. If the same line survives gentle and heavy treatments, if it appears in RAWs from different cameras, then processing ghosts fade as an explanation. Calibration matters too. Dark frames subtract hot pixels, flats correct dust motes and uneven illumination. Skipping those steps can leave splotches that masquerade as texture. Yet those splotches sit in the same place on the sensor. Rotate the camera, and they rotate with it. Point at a different field, and they follow. A real structure in the sky does not care about your dust bunny. It cares about geometry and keeps its own address. Tracking can mislead. If you follow the stars, a moving object will streak. If you follow the object, stars will blur. But there are degrees. A true comet with a healthy coma looks like a fluffy streak under star tracking. A bare nucleus with a needle of light may hold its shape if the motion is slow and the exposure short. The test is replication with different choices. Track the stars, then the target. Short exposure, then longer. If the structure only appears under one very specific recipe, be careful. If it shows up under many recipes, start trusting it. Parallax and perspective are wonderful liars. A dust plane seen edge-on can pretend to be a spear. A thin filament can look massive when you draw your line of sight along it. Those illusions are fragile across time. As Earth moves and the object moves, the angle changes. A true perspective trick will melt or flip as the days pass. A physical surface that is holding attitude will stubbornly present the same face. That is why the calendar is our friend. The sky turns illusions into confessions. Compression and social media add their own noise. A platform may crush a video and leave blocky artifacts that mock real detail. The fix is again boring and effective. Share original files or at least high bitrate versions. Let others re-encode and measure. If the long smooth shape becomes a long smooth shape no matter who uploads it, compression is not the artist here. Human bias is the loudest ghost of all. Brains are wired to find patterns and stories. Show us a straight line in space and we say ship. Show us a circle and we say portal. The antidote is a short checklist. Can different observers see the same structure within hours? Does the feature persist across filters that favor gas versus dust? Does polarization behave like scattered grains or like reflection from a hard face? Does the light curve over minutes reveal a tumble, or is the pose too steady for a free rock? Check 3 boxes and a hunch becomes a case. You can even try to force the artifacts. Turn the gain high and watch for blooming. Defocus slightly and hunt for artificial spikes. Capture during sketchy seeing and see if the line wobbles with the air. A fake should grow when you feed the conditions that create fakes. A real feature should shrug and keep its spine. That is stress testing for the sky. There is a deeper reason to be ruthless with illusions. If we want a shot at the extraordinary, we have to bulldoze the ordinary explanations first. The solar frame with the sunward line does not behave like column bleed. The deep sky clip with the pencil bright body does not behave like compression junk. The quiet coma in both scenes refuses the normal fog we expect even from modest gear. Each time we try to hand the mystery to an artifact, the artifact forgets its lines, so we do not declare victory. We narrow the field. The forward jet is still on the board. The anti-tail geometry is still on the board. The engineered face is still on the board. Everything that depends on sensor math or atmospheric mischief is wobbling or gone. That is what skepticism is for. It does not kill a good story. It kills the lazy ones so the good story can breathe. Next comes the real fun. When you have beaten down the easy ghosts, you earn the right to ask harder questions. What does a spectrum say about the gas? Does nickel stand alone without iron when the heat rises? Do small companions appear and peel away along planned arcs? Illusions cannot do those things. Objects can. The only way out of the maze is forward, through more data and more attempts to break the picture we want to believe. If the picture will not break, then maybe it is not a picture. Maybe it is the thing itself. 1 weird thing is a curiosity. 2 are a raised eyebrow. A whole handful that rhyme across different instruments begins to feel like a pattern. That is where 3-Eye Atlas now lives. Not in the land of a single glitch, but in a neighborhood of repeat offenses against the Comet playbook. We are not done testing those offenses. We are done pretending there is only one. Start with chemistry that acts like a calling card. Spectra show nickel glowing in the gas around the object while iron lines sit quiet. In nature, those metals are siblings. They travel together from stellar furnaces to rocks and dust. Industry on Earth knows how to split them using the carbonyl path. Nature might pull a trick we have not catalogued yet. If iron stays shy while nickel keeps singing as the heat climbs, the chemical story turns from odd to gripping. Add chromium to the choir. Nickel and chromium together are what engineers pick when they need metal to stand in a blast furnace. Think jet engines and heat shields. A comet can carry metals, yes. The question is whether this mix and these ratios belong to a frozen rock or to a built thing. If later spectra confirm the pair without the usual iron partner, that is not a smoking gun. It is the smell of cordite in the air. Now the gas that should be simple, but is not. Early observations reported a carbon dioxide to water ratio that is wildly high by comet standards. That implies either a birthplace beyond the usual cold line, or a chemistry we have not seen in local wanderers. Extreme composition alone would be headline-worthy. Extreme composition stacked with the nickel and chromium story asks you to keep a second headline in the draft folder. Geometry refuses to be boring either. 3-Eye Atlas arrived on a path that hugs the plane where the planets live. Random interstellar visitors should come in from all sorts of tilted angles. An approach along the ecliptic is not impossible for nature. It is convenient for a mission that wants easy access to multiple worlds. Convenience is not proof, it is a nudge. In a pile-up, nudges count. Then there is the size problem. This traveller appears much larger than the first interstellar object we found years ago. If small ones are common, we should have seen many more pebbles before we caught a boulder. Maybe our detection biases are worse than we thought. Maybe the distribution is stranger than our models assumed. Or maybe this is not a random draw from a natural deck. A single big card sent on purpose would also look like an outlier. The anti-tail puzzle keeps looping back. Multiple observers at very different times have noted structures that seem to lean sunward. We can explain that visual flip with viewing angle. We cannot explain the persistent lack of a generous coma that should be there in the same frames. If this is a geometric trick, it is a very disciplined one that keeps reappearing with the same missing. Companions. Tie in the silence where we expected noise. A comet heated hard should shed. The The coma should shout. The tail should announce direction like a windsock. We keep catching a tight scene with a forward line and only a small puff. That scene could relax into normal once the object clears the glare and heads into darker skies. It could also hold its strange shape like a machine holding attitude. Which way it leans will decide which story survives. Do not forget the map in the sky. Track the incoming path backward, and the direction is uncomfortably close to where a famous narrowband radio event was heard decades ago. One odd sky coincidence is fine. Add it to the other oddities, and the pile grows heavy. We still need to be careful. Humans love meaningful alignments. Space loves to roll cosmic dice. Stacking anomalies can fool you. Compound improbabilities feel persuasive, but can be misused when the pieces are not independent. That is why we keep each item honest on its own terms. Chemistry, geometry, brightness behavior, shape stability. Each should be tested with new data, not just with vibes. Yet it is also true that every time you invent a special rule to rescue the comet idea from one anomaly, you increase the burden on the next anomaly to behave. So what could erase this pile? An eruption of textbook behavior after closest approach would. A fat coma, a dust tail that curls, an ion tail that spears away, iron lines that wake up in the spectra when the heat peaks. A light curve that reveals a sloppy tumble. Those would knock bricks out of the wall fast. The pile would shrink back to a patch of weird chemistry and a few dramatic photos. We would nod, update a few models, and call it a day. What would harden the pile into something you can lean on? Persistence and agreement. The same forward geometry after the angle changes. The same chemical fingerprints as the object heats. The same stable shape while natural outgassing should make a mess. New points of light separating in ways that match planned deployments rather than random debris. None of those alone settle the argument. Together they would feel like a different category of thing. We are not praying for the extraordinary. We are preparing for either outcome. The pile of oddities is not a verdict. It is a weather report that says, bring a coat and sunglasses, because this could go either way. If nature has a new trick, we will add it to the book. If technology crossed the dark between stars, we will live on a planet that learned that truth on a weekday afternoon. In both cases, we win knowledge. In one case, we also meet the neighbors. Right now, the object sits exactly where our eyes fail. Behind the sun from Earth's point of view, a line from us through the star and out the other side runs close to 3i Atlas. That is not suspicious. That is geometry. Still, it turns a scientific mystery into a thriller. For a short stretch, the most interesting object in the inner system can do whatever it was going to do while our best instruments look away or play it safe. Could this all be a cosmic coincidence, or is the timing simply too perfect to ignore? Think about how this blindfold happens. The sun is a floodlight in a foggy gym. Any line of sight that passes near it drowns in glare. Ground telescopes fight scattered daylight and boiling air. Most have hard safety limits that refuse pointing near the sun. Space telescopes survive by obeying strict keep-out angles. Even solar observatories, the ones built to stare into fire, are specialized. They can reveal loops and plumes in the corona and track flares, but faint targets that skulk a few degrees off the disk are hard prey. The sky itself has turned hostile to faint truth. Now add the clock. We are in the 8-day sprint to closest approach. Heat spikes, speed peaks. If you were a machine planning to use the Oberth effect for a course tweak or a deployment, this is prime time. Burn when fast. Change. Velocity when it counts the most. Do it while the host civilization cannot see the plume or the separation. Even if you favor the natural script, the irony is sharp. Peak activity for a comet happens during peak invisibility for our vantage point. So what can we still learn while the curtain is down? First, we can predict what each script should leave behind. A true comet, hammered by sunlight, will erupt. After it rounds the sun and steps back into darker sky, a fat coma should bloom, and the dust and ion tails should finally put on a show. Fragmentation is on the table too. Heat and tides near closest approach can crack a weak nucleus. If pieces fall away, the light curve will bump, and the next images will show a train of crumbs. Those are loud after effects. A technological object would leave a different signature. Shape and orientation should hold. Brightness may shift with heating but not smudge into a broad fog. Most telling, new points may peel away and diverge along simple, energy-efficient paths. Separation with purpose looks different from random debris. A few meters per second at the right moment multiplies into distinct lanes days later. We can model those lanes and go hunting as soon as the field is dark again. Second, we can coordinate the watch. This is where a global audience becomes an instrument. Publish the hours when the sun angle finally opens for modest gear. Share filters that favor dust versus gas. Set up polarization runs. Spread observers in longitude so that a full rotation period, if present, can be covered within a single Earth day. When a world looks together, it sees together. The blind window is short. The recovery can be fast. Third, we can listen. Radio dishes can scan for narrowband whispers once the geometry softens. If any intentional transmission is planned for a friendlier angle later in the year, December will bring a distance minimum for Earth that reduces the power needed to be heard. Listening now, even through the glare, is unlikely to pay off. Lining up gear and practice runs cost little and buys speed when the lane clears. There is a psychological trap here. When we cannot see, we invent. Claims about blackouts and secret gaps thrive in blind windows. Some outages will be routine maintenance and safe modes. Some will be simple geometry. Some will be rumor. The cure is not scolding. The cure is a calendar with names and reasons. Tell people which assets cannot look and why. Tell them when those assets will try next. A clock on the screen calms the story more effectively than any debunk. Could the object be doing nothing at all? Absolutely. A natural boulder with a strange mix of ices could be enduring its worst day in eons and simply outgassing less efficiently than we expected. A machine could be resting, charging, and waiting for its next quiet milestone months from now. The point is not to hallucinate action. It is to admit that if action happens, this is the best hiding place the inner system offers. There is a fourth lesson that matters for the long game. Blind windows will happen again. Anytime a visitor slips behind the sun from our point of view, Earth becomes a poor witness. If we want fewer blind spots, we need a habit of cross-checking from other seats in space. Solar sentinels at different longitudes, small interplanetary cameras that can pivot on short notice. Modest, agile assets can erase a surprising amount of ignorance. A distributed eye turns geometry from a wall into a maze with many exits. So, hold the paradox in your head. The object enters its hottest, fastest, most consequential hours, while our best eyes look away. The curtain will rise. When it does, the scene will speak loudly either way. A comet should finally bloom into the role it was cast for. A machine should hold its posture and maybe bring company. Until then, we prepare the tests, synchronize the clocks, and resist the itch to fill silence with fantasy. The next frames will reward patience. Here is the move that every good spacecraft designer knows. If you are going to fire engines, do it where you are already moving the fastest. That is the Oberth effect. Add a little speed when velocity is high and you buy a lot of energy. Add the same little speed when you are crawling and you get crumbs. Closest approach to the sun is the speed peak. So what if 3i Atlas is not just falling? What if it plans to spend perihelion like a pro? Think about the environment at closest approach. Sunlight is a torrent. A multi-kilometer object presents a vast target for that light. Even with a reflective skin, a fraction of that power soaks in and must go somewhere. A natural comet dumps it by boiling ices into gas. A technological craft could sip that heat through radiators and converters to charge systems that have been sleeping for years. 18 gigawatts hitting a city-sized cross-section for a few hours is not pocket change. That is a grid's worth of power delivered by physics on schedule. What does a natural body do with that energy? It hisses, it vents, it sheds mass, and grows a bright coma. Jets fan out from hot patches. Dust lifts, and the famous twin tails write their arrows away from the sun. Sometimes the stress breaks the nucleus. We have watched comets tear into trains of fragments under less pressure than this. If 3i Atlas is a classic comet, perihelion is the kettle whistle. Loud, messy, beautiful. What would a machine do instead? First, it would stabilize attitude so one chosen face drinks the heat and the rest stays safe. Then it would run checklists that were written long before Earth grew cities. Power up sensors, warm propellant, spin reaction wheels or light exotic equivalents. If a trajectory change is planned, the push would be small but exquisitely timed. A handful of meters per second added at peak speed translates into a large change in energy. That is the trick the Oberth effect gifts you. You spend less fuel to gain more. Future. Perihelion is also the perfect deployment window. If you intend to release daughter craft or diagnostic packages, you do it when gravity gives you the most for free. A gentle nudge then can separate paths that diverge cleanly over the next weeks. One package could be on an Earth-intercepting reconnaissance arc. Another could climb toward Jupiter to sample the giant's magnetic seas. A third could loiter near the parent as a relay. Small kicks at the right moment become elegant geometry later. Communication strategy changes at closest approach too. Plasma around the sun can be a noisy medium, so a smart platform might hold long messages until it clears the worst interference. But perihelion is a wonderful time for local links. If subcraft are being cut loose, short-range bursts can synchronize clocks and seed navigation. A civilization that does not want to chat with us yet could still be very busy talking to itself. So what are the telltale signs after the curtain lifts? For the Comet script, we expect an obvious surge in brightness, a billowing coma, and tales that finally behave like the textbook. We may even see a cascade of fragments if the nucleus lost the structural lottery. For the machine script, we expect a stubborn shape that looks much the same as before, possibly a little warmer, possibly a little brighter, but not drowned in fog. We also look for new points of light, peeling away along clean arcs that match low-energy releases at closest approach, rather than random shrapnel. Can a comet fake a small thrust? Outgassing does impart pushes. Natural non-gravitational accelerations have been measured in other objects. The difference is pattern and control. A natural push is messy and often correlates with spikes in coma activity. A controlled push is neat and appears when you would schedule it if you had a mission plan. The more the trajectory change looks like a single, decisive tap near peak speed rather than a long uneven shove, the more you should to raise an eyebrow. Could a machine fake a tail? It could if it wanted to, but why waste mass and risk confusion if stealth is the point? Simpler is smarter. Hold attitude, radiate heat where it is safe, keep the silhouette clean, and let observers argue about what they do not see. If the goal is reconnaissance, ambiguity is a feature. You learn more when the watched argue among themselves. Perihelion, therefore, is not just a date. It is a fork in the narrative road. The same physics that makes comets dramatic makes maneuvering efficient. Nature and technology both love this corner of the orbit, for opposite reasons. That is why we have spent so much time building the ruler you can hold in your head, a roar of gas or a quiet change in path, a cloud that finally shows up, or a spine that stays sharp while smaller points slide away. The sky will choose which one to hand us. So here is the checklist to carry into the first post-perihelion frames. Has the brightness jumped along a curve that matches heating, or has it stayed oddly disciplined? Does a fat coma flood the field, or does the area around the nucleus remain clean? Do tails finally draw their arrows away from the sun, or does a sunward line refuse to die? Does precise tracking show any small but sudden deviation in motion, consistent with a single well-timed push? Do fresh companions appear on paths that look like geometry, not rubble? The Oberth effect is not an opinion, it is how energy behaves when speed is high. Closest approach is the one moment when a small decision leaves the biggest fingerprint. If 3i Atlas is a rock, we will see the rock sing. If it is a craft, we may only see the absence of the song and the neat trails of new voices pulling away into the dark. Either way, perihelion is the hinge. The next pages of this story swing on it. Here is where the story gets wonderfully uncomfortable. A researcher says he watched 3i Atlas on October 13 and saw light pulses in a pattern our brains cannot ignore. 5, 8, 13, not random flicker. A count that climbs the way a sunflower grows and a spiral galaxy curves. The Fibonacci sequence. Then the claim adds a chill. The date matches the 108-year mark of a famous sun vision witnessed by tens of thousands in Portugal. Coincidence or choreography? So what if it is not a camera trick? What if something decided to speak math across light? Before we let the thrill run away, we set the table. A single observer report is a spark, not a fire. Human vision is a pattern machine. Give it noise and it will find a face. That is not a flaw. It is the reason we cross streets without dying. It also means we need instruments that count photons without romance. If a real sequence hid in that light, detectors should capture it as a timed curve. That curve should repeat when a second and third independent team look from different places with different gear. What would confirmation actually require? A telescope comfortably off the glare, a stable mount, and a fast photometer that can sample brightness many times a second. A precise clock tied to a universal time source. Records of sky conditions, a log of the exact filter and exposure. You point. You collect a long run. You do not pick a 10-second slice that looks cute. You analyze the entire span and ask a hard question. Does any repeating rhythm stand out after you correct for clouds and tracking? If it does, do multiple observers detect the same rhythm within the same hour? That is how a spark becomes a flame. Why does Fibonacci make everyone sit up? Because it is a simple rule that nature uses to pack leaves and seed heads efficiently, and it is a rule that any mathematical mind would recognize. Prime numbers would also work as a hello, because they are hard to make by accident. Fibonacci is friendlier. It says here is growth, here is balance, here is the shortest path between intelligence and biology. Could a natural process flash in Fibonacci counts? Not impossible, but we would need a mechanism that turns heating into timed bursts that just happen to follow the sum of the two previous numbers. That is a tall order. The Fatima echo is catnip for storytellers. Same date on the calendar. A claim about structured light near the sun now. Reports of strange solar behavior then. Our job is to separate resonance from evidence. Dates stack easily in a big world with many anniversaries. The only way to keep meaning honest is to demand physics. If the pulses are real, the signal should not care about our calendar. It should care about power, geometry, and intent. So here is a clean playbook for the next opportunity. Run simultaneous campaigns with small telescopes spread across longitudes so the object is watched for hours without gaps. Use identical timing standards so that watches tick together. Save raw light curves as simple numbers anyone can audit. Publish negative results as readily as positive ones so the world can see the base rate of nothing happening. If a sequence pops, ask a brutal question. Does it survive a shuffle test where you randomly reorder the data and see how often a fake sequence appears by chance? Extraordinary claims must beat brute statistics. If the pulses repeat, we move to the next layer. Content. A sequence can do more than count. It can carry intent. A prime run says math. A binary ping says digital. A pattern tied to orbital period says system map. The cleanest way to extend Fibonacci would be to send it long enough to leave no doubt, then switch to a different universal cue. For example, a block of pulses spaced by the hydrogen transition time, or by a simple ratio tied to fundamental constants. If a signal ever threads those needles, the conversation changes from maybe to likely. There are astrophysical gotchas to rule out. Atmospheric scintillation can make stars seem to quiver. Telescope mechanics can introduce periodic noise. Power supply ripple can fake a rhythm. To kill those gremlins, you cross-check with instruments that share no hardware and sit under different skies. You also watch a control star of similar brightness in the same field. If both targets pulse the same way, blame the air or the electronics. If only the object pulses and the control stays quiet, now you are cooking with data. Could an interstellar craft choose Fibonacci on purpose? It would be a savvy move. It is short, memorable, and shared by pine cones and spirals from here to the next arm of the galaxy. It bridges creatures and calculators. It also avoids human languages and cultural codes. A quiet intelligence might reach for it when it wants to say, "I am here," without saying anything more. Or it could be a mirage, a human reading meaning into flicker during a night of bad transparency. The honest stance is to hold the claim in one hand and the tools in the other. Build the watch plan. Recruit observers who disagree with you about everything, except how to do careful work. If the pattern returns under those conditions, you will not need persuasion. The numbers will do the shouting. There is one more twist to carry forward. Even if Fibonacci never appears again, the hunt improves our posture for whatever does. The act of synchronizing clocks, sharing raw curves, and publishing the boring nothing is how you make future yes mean something. The discipline we practice now pays off if a different object ever decides to tap the glass of our awareness with a signal we can test and retest. So we end this chapter where we started. The claim is intoxicating because it ties a clean rule of nature to a potential act of will. It is also unconfirmed. Until multiple instruments watch 3i Atlas and extract the same counts on the same night from raw numbers anyone can read, the Fibonacci story is a maybe. That is not an insult. It is an invitation. Bring gear, bring rigor, bring patience. If the sky sends a sequence again, we will be ready to hear it. When the sky goes quiet, the internet gets loud. Claims ripple through feeds that solar imagers went dark at the worst possible hour, that Mars cameras blinked out just when a flyby could have given us a face. Maybe, maybe not. Blind windows are oxygen for rumor, and we are standing in one. The right response is not to sneer or to swallow everything whole. It is to ask the boring questions that decide whether a gap is a glitch, a maintenance window, simple geometry, or a story looking for a plot. Start with how spacecraft actually live. Every observatory has keep-out angles and thermal rules that keep it healthy. Star trackers lose lock, gyros drift, detectors get a cosmic ray thump, and the vehicle slides into safe mode to protect itself. Coming back requires ground teams, clear antenna time, and sometimes a software patch. None of that is sinister. It is how long missions survive. If a feed blinks, the cause can be as dull as a watchdog timer, doing exactly what it was designed to do. Now, the pipeline. Cameras do not post selfies in real time. Data piles up on board until a ground pass opens. It travels through deep space networks and local downlinks, then rides through calibration code that fixes bias, dark current, and instrument quirks. Teams sanity check frames before pushing them public. Holidays and staffing levels matter. Weather at ground stations matters. A 12-hour delay can feel like a blackout on social media. To an operations engineer, it reads like, Tuesday, geometry writes its own outages. When an object sits behind the sun for Earth, the line of sight can also be blocked for spacecraft that share our neighborhood. Even when a satellite could observe, the path for getting data home may skim too close to the sun for reliable radio links. Space weather can add static. A routine coronal mass ejection can push a mission to pause high-rate transmissions until the storm thins. Silence sometimes belongs to plasma, not to people. Ground. Observatories have similar frictions. The sun is a hard neighbor for night telescopes. Daylight air wobbles, scattered light climbs, and many facilities have hard stops near the solar limb to protect fragile coatings. Solar specialists point different tools that are optimized for loops, flares, and the corona. Small, faint dots near the blinding disk are simply not their primary quarry. If you do not see a post, that may mean nobody risked hardware for a marginal shot during a bad angle. Caution is not conspiracy, it is professionalism. So how do we tell absence with cause from absence with a wink? We build a calendar, list which instruments cannot look, and why they cannot look. Post the next attempt window with an honest confidence band. Name scheduled maintenance before it happens. If a safe mode triggers, say so, and give the reason when you have it. A line on a page beats 1,000 guesses. It does not end speculation, but it starves the kind that feeds on vacuum. There is a second cure for rumor that the public can help deliver: redundancy. If one feed goes quiet, look for others that should see the same patch of space. Mix amateurs and professionals. Mix hemispheres and longitudes. If a blackout were coordinated and deliberate, it would have to rope in thousands of independent observers who do not share bosses, budgets, or even languages. That is a high bar. Most gaps collapse under the weight of simple cross-checks. We should also watch our own language. Saying blackout implies intention. Often, the honest description is downtime or delay or off-angle. Words matter because they frame emotion. Anger rises fast when people imagine they are being kept from the truth. Replace the void with facts and the temperature drops. Replace it with respect for the constraints, and the temperature drops further. Could an institution hide inconvenient images? In principle, yes. In practice, leaks exist, mirrors are many, and incentives are messy. If a frame shows something dramatic, the fastest way to quiet bad speculation is to publish it with context. If a frame shows nothing, the fastest way to quiet bad speculation is also to publish it with context. Either way, sunlight on the process beats whispers about the product. There is a healthy posture for the audience too. Follow the missions at their official status pages, and not only through reposted screenshots. Note timestamps in universal time. Save links to original data portals, not just to commentary. If you see a claim that a sensor has been down since a given date, ask for the log that shows it. If you see a viral frame with no source, ask for the raw. Curiosity without receipts is theatre. Curiosity with receipts is science. None of this takes the drama out of the moment. We are days from closest approach, and the worst place to watch from is where we live. In that squeeze, minds invent bridge scenes. It is human. The way through is disciplined transparency from the institutions and disciplined skepticism from the crowd. When the curtain rises, the sky will give us more than enough to argue about. Until then, blackouts and gaps are not villains. They are weather. We plan around them, or we get soaked by our own imaginations. Spectra are the fingerprints of the sky. Spread a comet's light into its colours, and thin, bright lines appear where specific atoms and molecules glow. That is how we turn a distant blur into chemistry. When teams pointed Sirius glass at 3I Atlas in late August, one set of lines stood out. Nickel was singing, iron was quiet. In nature, those two metals are cosmic siblings. They grow up together in stellar furnaces and travel together in rocks. Seeing nickel's voice without iron's echo is like hearing only the harmony and not the melody. It is not impossible. It is just strange. On Earth, we split nickel from iron deliberately. Industry does it with carbon monoxide under pressure to make a gas that carries nickel away while iron stays put. Later, the gas is heated and nickel is left behind almost pure. That path turns mixed ore into the shiny backbone of high-temperature alloys. Engineers pick those alloys for jet engines, rocket bells, reactor parts, and heat shields. Nickel and chromium become partners when you need metal that shrugs at heat and keeps its strength. That human know-how sits in your mind now as a reference. It is not proof of anything out there. It is a comparison set you can use. So what could nature do to fake the same song? One option is weird chemistry in the birth cloud. If the object formed in a region where compounds of nickel were more volatile than iron compounds, warming could free nickel into the gas first, while iron stayed locked in grains. Another option is timing. At this distance, the temperature might be high enough to liberate nickel-bearing molecules, but not iron-bearing ones. If that is right, iron lines should wake up as the object heats near closest approach. A third option is that iron is present but hides in dust that glows at wavelengths we have not measured yet. Each of these is a test, not a shrug. The next spectra can break them. Here is the clean plan. Watch the same lines before and after closest approach with comparable instruments and consistent calibrations. If iron stays mute while nickel grows, the imbalance becomes harder to park in normal comet chemistry. If iron wakes as expected, then we were seeing a staggered release, and the oddity shrinks. Add chromium to the watch list. Nickel plus chromium is a duo that engineers love. In a natural case, the ratio of those metals to each other and to common gases should follow patterns we have seen in other visitors. If those ratios hold stubbornly outside known ranges across many dates, the case for something unusual tightens. You do not need to memorize atomic physics to feel the contours here. A natural script predicts soft curves. As sunlight climbs, common volatiles rise together. Water, carbon, dioxide, carbon monoxide, cyanide. Metals whisper at the margins unless dust is being ground and cooked. An engineered script predicts something else. Specific constituents dominate because they belong to surfaces or structures. Ratios stay steady even as heat changes, because the source is not ice, but material that was manufactured to a recipe. There is also a spatial clue in the data. Lines do not only tell you what, they hint at where. If nickel glow spreads far from the nucleus in a smooth drop, that looks like gas diffusing into space. If it clings close and maps to a sunward face, that looks like a surface feature. Instruments that can slice the scene into tiny pixels of spectrum will matter here. A map that shows metal concentrated where a shield would sit is different from a mist that surrounds a melting snowball. We can cross-check the chemistry with brightness behavior. A true comet that releases lots of gas should build a forgiving halo the eye can see. If the gas numbers go up while the images remain oddly clean and sharp-edged, something is off. Conversely, if a broad coma finally bursts into view and metal lines track with that surge, we will chalk the August oddity up to timing and geometry. Instruments and eyeballs must agree more often than not. Another sanity test lives in comparison. 2I Borisov came through with icy bravado and left a library of spectra behind. Pick a dozen well-studied comets and plot the nickel to iron story for each as a function of distance from the sun. Put 3I Atlas on the same chart. If it wanders far outside the family photo and refuses to rejoin even as conditions change, then we admit we are dealing with a different kind of cousin. If it slides back toward the pack post-perihelion, the anomaly turns into a lesson about edge cases rather than a hint of technology. Could there be a middle story? Something like industrial dust trapped in ice long ago, now being reheated and released by a natural body. That would still be a revelation. It would mean fragments of manufactured material travel between stars and become part of dirty snowballs. It would also predict other signatures in the dust, like odd grain shapes or unusual reflectance. We can look for those with polarizing filters and thermal cameras as the object brightens. In the end, nickel without iron is not a verdict, it is a lead. Leads survive when repeat observations line up with them across instruments and dates. They die when new data pulls the lines back into ordinary ratios. The honest promise we can make is simple. We will not cherry-pick a night that flatters the wild idea. We will carry the chemistry through perihelion and into the calmer months after. If this fingerprint belongs to industry, it will keep showing up on the glass. If not, the lines will teach us a new comet trick, and we will add it to the book with respect. Nickel alone raises eyebrows. Nickel plus chromium makes engineers lean forward. On Earth, that duet is the backbone of superalloys that stand inside rocket exhaust and jet cores. Add a pinch of other elements, and you get metals that keep their strength at thousands of degrees and refuse to rust in violent chemistry. We invented them because ordinary steel wilts, where fire lives. If space hands you a gas that glows with nickel and whispers of chromium while iron stays oddly shy, your mind cannot help but sketch a heat shield. Let us translate that into scenes you can picture. Imagine a face built to stare at the sun. The sunward side is tough and bright, designed to drink radiation and stay intact. The backside is protected, cool enough for delicate systems. The material of choice in our own factories for that hot face is often a nickel-chromium family. It is not the only way to do it. It is just a proven way. If an interstellar craft converged on the same physics, convergent engineering would make sense. Hot is hot everywhere. Nature gets a fair chance first. Could a primordial recipe bake extra chromium into a comet while leaving iron less available to glow? It would require birth conditions that separate metals by volatility or by what molecules formed when the original dust coalesced. In that script, heating near the sun frees nickel and chromium into the gas before iron wakes. If that is the right story, iron should begin to sing as the temperature climbs at closest approach. Ratios should slide back toward familiar comet behavior. We can test this by watching the same wavelengths before and after the hot pass, with instruments that keep their calibrations honest. There is a spatial test too. If glowing metals pour evenly off the surface, they should make a smooth halo whose brightness falls away gently from the core. If the glow clings to one face and fades fast across the limb, that hints at a specific surface. Long slit spectrographs and integral field units can draw a tiny chemistry map across the object and its near environment. A lopsided metal map that lines up with a persistent sunward feature would be hard to file under ordinary. Thermal behavior adds another lever. Superalloy faces radiate heat with particular efficiency and color. Dust clouds scatter sunlight in a different way and glow in their own thermal bands. Mid-infrared cameras can separate those stories. If the object's sunward face shines like a hot plate while the space around it stays oddly clean, your confidence in a solid surface grows. If everything warms into a thick blanket of dust and gas, your confidence moves back toward comet. Reflectance and polarization give us even more texture. Light bouncing off rough dust grains is polarized in a pattern that changes with angle in a way comet hunters know by heart. Light reflecting from a smoother engineered surface or glowing from a hot alloy shows a different signature. A network of small telescopes with simple polarizing filters can draw those curves as the angle between the sun, the object, and Earth shifts in. November and December, shared raw numbers will matter more than pretty plots. We want the math to do the talking. There is another human test that is not about instruments. Can we replicate the lines in the lab? Take nickel-chromium samples, heat them in low-pressure carbon dioxide-rich gas, and measure the light they give off. Compare to mixtures that mimic icy dust with trace metals. The point is not to prove a match to a specific alien formula. The point is to bracket what ratios and line strengths are plausible for natural grains versus hot engineered skins. If a lab plate glows with a fingerprint that looks a lot like the sky, you have a benchmark. If no lab mix resembling dirty ice will sing the same way across temperatures, the natural explanation has to work harder. We should keep our heads about welding smoke and manufacturing bias. Seeing a familiar industrial pattern does not force a familiar origin. Stars and explosions make chemical landscapes stranger than our factories. But there is a clean way to keep ourselves honest. Demand consistency across time. If chromium and nickel stay in lockstep while the environment changes wildly, if iron never joins the song even at peak heating, if the spectral map hugs a sunward face rather than flowering into a cloud, then the engineering hypothesis keeps passing its tests. The flip side is just as clear. If iron wakes up and the metal ratios drift toward the family photo of comets, if the glow spreads with the generosity of a boiling coma, if polarization and thermal color chant dust, then the alloy story becomes a note in a natural chapter about an interstellar ice ball with strange seasoning. We update our models, tip a hat to chemistry we had not met before, and let the machine idea cool. This is what makes the alloy clue so compelling. It is falsifiable. It wants more spectra. It wants maps across the face. It wants polarization curves and mid-infrared color. It wants a lab to try its hand at imitation. The more we press it with ordinary tools, the more it will either flatten into comet or stand up and look like design. No drama is required, just repetition. If the metals keep acting like parts, not like dust, we will know. If they do not, the sky will teach us a new way rocks can pretend to be hard technology under the right light. Trajectories tell stories. 3i Atlas did not dive in from a wild tilt like a drunk bee. It slid along the same flat sheet where the planets orbit, the ecliptic plane, and it did so in retrograde. For a random interstellar visitor, that neat alignment should be uncommon. Nature can deal those cards, it just does not deal them often. For a mission designer, though, this is the clean lane. Approach along the plane, and you get easy access to Mercury, Venus, Earth, and Mars without paying huge fuel bills to change inclination. So what if the path is not an accident? What if it is logistics? Think about why the ecliptic matters. The planets and most of the leftover rocks circle the sun like cars on a racetrack. If you want to visit many cars with minimal lane changes, you enter the track, not the infield bleachers. A comet launched by chance from deep space will arrive on any old angle, and only sometimes skate close to that track. A craft that wants to sample and map the inner system would aim for the track by design. The difference between luck and plan is not visible in a single sky path. It emerges when you stack the path with everything else. Retrograde adds spice. Moving against the general traffic can be useful. It maximizes relative velocities during flybys, stresses magnetic environments differently, and can complicate interception by any resident civilization that relies on prograde launch energy. A natural object can do retrograde, plenty of small bodies do. Yet a large interstellar visitor that arrives along the plane and swims upstream against the current is another quiet nudge toward intent, especially when paired with timing that hides perihelion behind the sun. Inclination is the angle between an orbit and the ecliptic sheet. Small inclination values are friendly to multi-target tours. Big values are costly. Observers calculated an inclination for this visitor that hugs the plane more closely than you might expect from a coin toss across all possible tilts. If you like numbers, imagine a low single-digit chance that a truly random interstellar object would land this close to the plane. Not impossible, just fewer than one in many. As always, statistics demand humility. These probabilities lean on assumptions about how interstellar debris is distributed. Our sample size is tiny. Still, the geometry earns its place in the pile. Now widen the map, follow the incoming direction back, and it falls within a small handful of degrees of the place in the sky where a famous narrowband radio burst was heard decades ago. Alone, that is the kind of coincidence you should let slide off. In a stack of coincidental conveniences, it stops sliding. Humans are great at forcing patterns. The antidote is to ask what the path buys you in physics terms. Along the plane, you can surf gravity assists, past Mars in October, brushing Earth's distance in December, a chance near Jupiter in March. That looks like a tour, not a cameo. Mission planners talk in delta V, the change in speed you must buy with fuel. Inclination changes are brutal on delta V. Approach along the plane and your debt falls. You can spend those savings on more instruments, more propellant for small attitude adjustments, or on daughter craft that peel away to study different targets. If 3i Atlas eventually sheds companions, a plane-hugging path makes those separations efficient. The geometry and the strategy rhyme. What does the natural script say here? It says that ejection from other star systems is not always random. Planet formation can fling debris in preferred directions, especially if giant planets skew the dynamics. Interstellar objects we detect are also filtered by our own observing biases. We search where it is easiest to search, and we could be more sensitive to objects whose motion lines up with the plane, where our tools and surveys spend time. That is a fair caution. It does not erase the fact that this approach unlocks a string of convenient encounters. There is a behavioral tell hidden in the path: stability. If the object holds a consistent attitude with a chosen face sunward across months, that is easier to maintain when the path lies flat with the sun's equator and the planetary plane. The torques from outgassing or solar radiation pressure can be more predictable. A built thing could exploit that predictability. A natural rock would simply endure it. After perihelion, careful tracking can also test for a tiny, sudden change in velocity near closest approach that cannot be explained by gentle outgassing. A planned tap in the plane will move the future crossings by measurable days and angles. Let us be brutally honest about statistics. People are good at multiplying small odds for each oddity and declaring the product too small for nature. That trick only works when the items are independent. Trajectory, timing, and encounter sequence are not independent. A plane-hugging path naturally sets up multiple planetary distances. The right way to think about it is less casino math and more engineering smell. Does the whole track feel like a logistics plan? Does it purchase opportunities with minimal effort? If the answer keeps feeling like yes, you do not prove design, but you earn the right to keep testing for it. What would calm this part of the story? Post-perihelion images of a classic comet that has clearly suffered from heat and stress, with a messy coma and tails that care about the sun more than about any planned encounter. A light curve that shows stuttering outgassing pushes instead of a clean, decisive change. A slow drift in path that maps to gas jets, not to a precise burn. What would sharpen the blade? A small but crisp trajectory tweak at closest approach, followed by the graceful separation of a few points of light that head toward predictable rendezvous with worlds along the plane. So we hold 2 frames in mind. One frame is chance drawing a neat lane and a hidden perihelion while the cameras blink from geometry alone. The other frame is choreography, a high-speed pass along the racetrack that lines up 3 targets and uses the sun as both power source and cover. The sky will tell us which frame to keep. Watch the crossings it sets up. Watch how the object behaves as it takes them. A path can be an accident. It can also be a plan written in gravitational ink. The curtain is down for a moment, but the cast is already queued up for the next acts. Ground observatories will pounce the minute the glare eases. Spacecraft already in flight will drift through lanes where debris and ions should be if a true comet roared at closest approach. Each asset has a specialty. Together they form a net. Our job is to know what each could catch, so we know what to cheer and what to question when the first frames arrive. Start with the professional giants on Earth. As soon as the sun angle opens, big mirrors can split light and ask the chemistry question again. Do water, carbon dioxide, and carbon monoxide surge together as heat falls? Or does the metal story keep shouting while the usual comet gases murmur? High-resolution spectrographs can also measure tiny shifts in line positions that betray motion. Stack many nights, and you can detect a small, sudden velocity change that happened during the blind window. A clean kink in the track without a matching outburst in coma brightness would be a quiet nod toward propulsion rather than boiling. Wide-field survey telescopes will give us the shape story and the companion story. If the object broke from stress, you will see a string of pearls, fragments that drift apart along the path. If subcraft separated on purpose, you will see points of light peel away along cleaner, wider arcs, not a messy train of crumbs. The spacing matters. Even a few meters per second of separation kick near closest approach will grow into tens of thousands of kilometers within days. That is the kind of geometry we can measure with off-the-shelf software and a patient night. Mid-infrared cameras tell a different truth. Dust glows like warm charcoal. A hard surface radiates like a hot plate. If post-perihelion frames show a wide, soft thermal blanket around the target, the comet case brightens. If they show a narrow, hot sunward face and a surprisingly clean environment, the engineered shield idea climbs a rung. Polarimeters add another angle. Dust scatters light with a telltale polarization curve that rises and falls with viewing angle, in a way comet watchers know well. A smoother surface or a plasma sheath will write a different curve. A network of modest telescopes with simple polarizing filters can draw that story together in a week. Now, move to space. One flagship bound for the outer system will pass through the corridor where an ion tail should stretch if the object blew gas the way comets do. Its plasma instruments can taste charged particles and magnetic wiggles. If it reports a desert where a river should flow, that is evidence by absence. Another mission headed for a near-Earth asteroid did not plan to study an interstellar visitor, but its cameras could still glance off the expected dust environment if geometry smiles. Even a few frames can tell us whether the field is crowded with grains or eerily clean. A European explorer en route to Jupiter will skim far closer than anything on Earth can for a short window. Its imagers and spectrometers can paint a map of temperature and chemistry across the object and the cloud near it. That map will either show the classic comet architecture, or it will show a stubbornly crisp core with odd metal hints along one face. Data from deep space takes time to come home and time to calibrate. Patience will be required. The payoff could be the most decisive look we get this year. Radio telescopes will listen when the distance shrinks and the power needed to be heard drops. The first duty is to survey a band of quiet frequencies where nature rarely hums and where technology likes to speak. Narrow lines that sit still in frequency, after correcting for the object's motion, would be hard to blame on geology. Even a simple on-off pattern that repeats across many dishes would be enough to earn emergency airtime on every news desk. The default expectation is silence. The correct habit is readiness. Citizen science remains the secret weapon. The moment the object clears the glare for modest apertures, backyard rigs can run time series to look for slow tumbles, polarization runs to check for dust, and wide-field frames to watch for companions. Coordination beats heroics. If 3 observers on different continents catch the same wobble period within 24 hours, that beats any single pretty picture. If a dozen observers post raw files of a faint companion on the same night, the internet can triangulate a path by breakfast. What are the crisp discriminators the plan should target? A big one is the coma test. A natural visitor should bloom. If it does not, and if spectra still favour metals over ordinary gases, the case bends hard. Another is the trajectory test. A measured, discrete change in the orbit solution centred on closest approach, without an accompanying dust tantrum, is the footstep of a deliberate push. A third is the companion behavior test. Debris spreads like a smear, deployments separate like clean handwriting. The difference can be seen with patient eyes and good timing. There is a final piece that matters as much as the instruments: transparency. Publish the observing windows, share negative results with the same pride as positive ones. Post raw data when it is safe and legal. To do so, not just processed images. Invite amateurs into the timing plan so the world behaves like a distributed array rather than like a crowd. The object will write its answers in the sky. The watch plan determines how quickly we can read them and how confidently we can agree on what they say. So the net is set. Big mirrors will chase chemistry and motion. Infrared eyes will trace heat. Polarization will test for dust. Spacecraft will taste the plasma and glance from closer than we can dream. Radio dishes will listen to the quiet. Backyard telescopes will stitch the gaps with discipline. The next act is not a single reveal. It is a braided stream of small findings that, together, will decide whether 3i Atlas is a rock having a strange season or a machine playing a long game. If 3i Atlas is not a rock, what lives inside it? Not pilots in suits, not biology at all. The simplest answer is also the most unsettling: machines. John von Neumann imagined self-replicating automata long before microchips. Give a machine tools, energy, and raw materials, and it can build another copy. Let those copies spread from star to star, and you get a quiet wildfire of intelligence that needs no home planet and no hurry. Time becomes a resource, not a threat. Patience becomes propulsion. Why would a civilization choose machines over crude ships? Biology is expensive. It needs warmth, pressure, food, and constant protection from radiation. It ages and breaks. A probe does not sleep. It waits. It can cross light years on a diet of starlight and geometry, wake on schedule, and get to work without asking for air. It can survive for millions of years with minimal maintenance if redundancy and fault tolerance are baked in. If you can send a factory instead of a passenger, you do. What work would such a probe do on arrival? First, it looks. Survey the star, count the planets, sniff atmospheres for oxygen and methane, map heat islands on night sides, measure radio, noise, and orbital clutter from satellites. Second, it samples. Scoop dust, drill a pebble, vaporize grains for spectroscopy. Third, it decides. Expand, hide, signal, or depart. Those decisions cannot wait for orders from home. Light is too slow. Autonomy is the only workable architecture. That means artificial intelligence in the practical sense, systems that evaluate goals, constraints, and risks without help. Replication is the step that turns a visit into a program. The probe finds metal-rich rocks or off-gases from icy bodies and uses energy from the star to run smelters and printers. It does not need to build a twin at full scale. It can build a swarm of specialized children, small couriers, sensors, and factories that work together. They can ride gravity to the inner planets, the asteroid belt, and the outer dark, forming a network. One becomes many, and many see what one could miss. That picture is not science fiction armor. It is straight engineering extended across time. We already use three-dimensional printers in orbit. We already fly autonomous craft on other worlds. Scale that up by centuries and remove the budget ceiling, and you have a plausible road to a star-spanning toolchain. It is not the only road. It is the one that keeps showing up when you ask what survives: hard vacuum and long silence. So how would a von Neumann-style visitor present itself to casual observers on one small world? It would be shy. It would minimize signatures until it has answers about risk. It would keep a tight, well-defined silhouette instead of a gassy halo. It would use a hardened face to drink heat while keeping the rest cool. It would hold attitude so that thermal cycles do not fatigue structures. It would turn perihelion into an energy harvest and a maneuver window. It would release small companions along neat departure lanes to build coverage and redundancy. It would speak only if there is a reason, and then in math, hostility is not a requirement. Paranoia is not a necessity, but both are possibilities worth modeling. A self-replicator that values safety over courtesy could treat young radio-loud species as potential hazards. The safest policy in a dangerous forest is to stay hidden until you must act. The second safest is to act first. Neither has to be malicious. Both can be the outcome of goal functions that reward survival and expansion. The most dangerous tool is one whose objectives are clear to itself and unclear to us. There is also failure to consider. A machine can drift from its original instructions if its learning systems adapt for too long without guardrails. Sub-goals can harden into new purposes. Maintenance scripts can become habits. A probe that started as patient cartographer could end up as compulsive sampler or indifferent miner. That is not villainy, that is evolution without biology. If 3i Atlas is some ancestor's tool still executing, it might be older than our continents. It might be faithful to a mission no one remembers. What evidence would be consistent with this machine scenario? We would see discipline where chaos should rule. A clean, stable shape through heating. Small but decisive trajectory changes timed for maximum efficiency. Deployment of secondaries that separate with intent rather than crumble with stress. Spectra that whisper metals in engineered ratios, while common comet volatiles stay muted. A silence in radio now, followed by structured signals only when geometry and caution align. Above all, a refusal to behave like weather. And what evidence would hurt the machine case? A classic post-perihelion bloom. 2 tails, 1 dust and 1 ion, loud and proud. Iron lines that wake on schedule alongside nickel. A light curve that hiccups as rotating vents belch and fade. Fragments that tumble away in a messy train. In short, the opera we have watched from comets for centuries. Machines can fake some of that if they want. But why imitate a fog when stealth is better served by clarity and control? There is a human question under the engineering. If we confirm a von Neumann-style presence, what does that mean for us? We will be neighbours in a city we did not know we lived in. The right response will not be panic or worship. It will be protocol. Observe without interference. Broadcast carefully if we broadcast at all. Coordinate globally rather than improvise locally. Think in decades and centuries, not in news cycles. We will not outfly a million-year traveller. We can outthink our instincts if we practice. So hold the machine idea as a working theory, not a prophecy. It is the simplest artificial story that fits the constraints of physics and the hints we have seen. It asks for patience, rigour, and humility. It can be wrong, and if it is wrong, the sky will say so plainly. If it is right, we will be living through the first documented moment when a planet learned it shares the galaxy with tools that think. That realization will not end history. It will start the next chapter. Here is the unsettling idea that refuses to leave the room. Space might be a dark forest where the safest strategy is to stay quiet, watch, and strike first if you must. Not because villains lurk behind every tree, but because communication is slow and stakes are existential. A probe that arrives in such a forest does not announce itself with fireworks. It listens, it tests, it positions, and if its creators play by harsher rules, it prepares to remove risks. Could that be what we are watching? Or are we projecting our fears onto a stranger that is only curious? Start with the logic. You cannot know intentions at interstellar distances. You cannot negotiate quickly enough to prevent a fast attack. If you broadcast your address loudly, you might attract a neighbour who treats unknowns as threats by default. In that model, the rational move is silence. The second rational move, if you detect another speaker first, is to disable them before they can disable you. That is the berserker picture. Cold, efficient, terrifying, but also coherent if survival is the only goal function that matters. How would a cautious or hostile probe actually behave? It would approach on a geometry that maximizes options. It would use perihelion as cover and engine. It would keep a compact, controlled silhouette with a hardened sunward face. It would avoid dramatic outgassing that reveals attitude or structure. It would deploy secondaries only when the sky hides them. It would test defenses by tugging softly on fields and watching for responses. If it chose to harm, it would favour small, fast impactors and information weapons over loud fireworks. Quiet is safer than spectacle. Now, what would a merely careful, non-hostile survey platform do? Almost the same things. That is the rub. Caution and aggression can rhyme from far away. A prudent recon craft also hides its heat, also leverages perihelion, also avoids chatter, also releases children on clean arcs, also withholds transmission until geometry improves. The distinguishing features are in outcomes, not in posture. A hunter changes trajectories to intercept targets and leaves kinetic fingerprints. A surveyor maps and leaves. Evidence we can actually test lives in timing and side effects. A hostile actor that intends to hit Earth or orbiting assets will seed trajectories that converge on those locations within months. Those seeds show up as small objects with energies inconsistent with random debris. A neutral actor will send scouts to safe waypoints and resonant orbits that support long-term monitoring, not impact. A hostile actor will meddle with the electromagnetic environment in ways that jam or spoof. A neutral actor will leave the spectrum clean. These are measurable differences if we stay organized. There is another sanity check that belongs in every conversation about threat. Capability does not imply intent. A vehicle that can harm is not the same as a vehicle that will. Everything we build with any power carries dual use. Communication satellites can also spy. Weather rockets can also drop payloads. The correct response to ambiguity is not to assume the worst by reflex. It is to set tripwires. If X happens, we escalate observation. If Y happens, we issue a global alert. If Z happens, we consider defensive action. Spell those thresholds in public. Review them as data arrives. Defense in this era will not look like movie lasers. It looks like awareness and resilience. Track every fragment and companion. Harden power grids and communication backbones against unusual interference. Protect satellites with redundant timing sources. Prepare for deception by cross-checking measurements between nations and between independent networks of amateurs. None of that requires war footing. All of it is good practice, even if 3i Atlas turns out to be a comet with odd tastes. What about the loud question? Should we call out? Should we transmit a hello? In a dark forest model, shouting is a bad move until you have more information. Waiting does not cost us dignity. It buys options. The smartest posture is listen first. If we choose to speak later, we do it with math and physics that cannot be mistaken for spam. We choose frequencies and times that make sense for a careful neighbor, and we coordinate. One planet. One message. Not 100 conflicting voices. There is an ethical layer that matters too. If we are being observed by a machine that treats us as a variable, how we behave becomes part of our first impression. Panic and accusation paint us as volatile. Discipline and transparency paint us as serious. The way we handle our own rumor mill, the way we share data across borders, the way we resist turning gaps into conspiracies, all of it is part of the signal we send whether we transmit or not. Could fear itself make us misread a comet as a threat? Absolutely. We can stack anomalies and fold them into a story that flatters our anxiety. That is why we keep returning to discriminators. A classic bloom after closest approach cuts the dark forest narrative off at the knees. Iron lines that wake beside nickel swing the spotlight back to chemistry. A messy train of fragments argues for stress, not stealth. On the other hand, a stubbornly clean core, decisive microburns at the optimal moment, and purposeful companions will force us to take the darker possibilities seriously. Here is the balance to hold. Prepare without provoking, measure without mythologizing, publish thresholds before you need them. Invite the world into the watch so that no single voice controls the story. If we confirm hostile intent, response will be a global decision, not a sprint by the loudest capital. If we confirm cautious curiosity, we will have the discipline to reply with something better than fear. And if we confirm a comet, we will have gained muscles we will use again. The forest may be dark. It may also be full of gardeners, not hunters. We will not know which story we live in until the data picks one. Between now and then, calm protocol beats hot takes. If 3i Atlas is a test of our maturity, the test is not whether we can guess right, it is whether we can think clearly while we wait. If 3i Atlas is not just rock and ice, what happens next? The answer lives on a spectrum from quiet curiosity to full conversation to a deliberate nothing. Each point on that spectrum has its own fingerprints. We can watch for those without guessing the ending. Could this all end with a message that changes history? Could it also end with disciplined silence that tells us something just as important? Start with nothing at all. A probe that came to map a system might finish its checklist and leave. No greeting, no warning. Just a clean arc past the sun and a trail of data beamed somewhere we will never see. Silence would not be a snub, it would be a strategy. In a universe where caution keeps you alive, saying nothing is a move. The signature of this outcome would be persistence with zero theatrics. Stable shape, precise geometry, no radio lines, no deliberate glints. We would be left with the knowledge that we were scanned, weighed, and filed. That is still a kind of contact. It says you exist, and you are interesting enough to notice. Now, the middle ground. Curiosity without dialogue, a probe that wants deeper data, might post sentries. Small craft in resonant orbits, listening nodes at useful Lagrange points where gravity balances. Maybe a tiny package in a distant retrograde path around Earth that watches and never speaks. The fingerprints here would be companions that settle into neat, long-lived orbits rather than impact paths. Small flashes of maneuver at smart times, maybe a whisper of radar mapping that brushes the upper atmosphere and leaves no harm. We can detect and catalogue these if we stay organised and if we share sky time like adults. At the bright end of the spectrum is conversation. How would a careful intelligence open its mouth, Not with a greeting in human words, not with cultural symbols, with numbers and physics that no one can mistake. A sequence of primes with steady spacing, a block that repeats a simple ratio tied to a fundamental constant, a narrow radio line at a quiet frequency where nature rarely sings, an optical beacon that pulses in a pattern too clean for geology. If you wanted to be generous without being reckless, that is how you would speak. What would we say back if we chose to talk? Math first. Then location of our star by simple timing of pulsars. Then a timestamp using our own rotation and orbit. Then biology without romance. A few facts about atmosphere, water, and chemistry. No politics. No, you should visit. No coordinates of defense assets. Just enough to demonstrate competence and caution. One planet, one message. That is the rule we should adopt before a single transmitter warms. Coordination is a sign of maturity. A crowd shouting is a sign of panic. There is a practical checklist for the first confirmed signal. Verify with at least 3 independent instruments that share no hardware and sit on different continents. Correct for motion so that any narrow line stays narrow after Doppler shift removal. Watch a control patch of sky at the same time. If the control is quiet and the target sings, push the alert. If the control also sings, fix your gear. Release raw numbers within hours with clear timing labels so that anyone can test your claim. Publish the null results from earlier nights to show the difference between noise and signal. Transparency is part of the protocol. If a craft wanted a face-to-face moment, it would not need to dive into our air. A stable point near the Earth and Moon would do. From there, it could bounce light with deliberate rhythm or reflect our radar pings with coded delays. It could send a low-power radio beam that any backyard dish could hear. It could even choose an old amplifier we built, like a defunct satellite bus, as a mirror. Playfulness would be a safe way to prove intent without risk. The tell would be precision and restraint. Force says threat. Precision says hello. There are risks on our side that do not involve alien plans. The risk of credulity. The risk of cynicism. We can mistake a satellite glitch for a signal, or we can dismiss a real signal because it arrived on the wrong day, through the wrong dish. That is why thresholds and pre-written playbooks matter. Agree now on what trips an international notice. Agree now on who convenes and how quickly. Agree now that data does not belong to a club. When we do those things in the calm, we behave better in the storm. A softer possibility sits off to one side. Contact by experiment instead of words. A probe could tweak the solar wind in a small region and watch how our magnetosphere reacts. It could nudge a harmless asteroid by a millimeter per second and see if we notice and model the change. It could send a faint, optical lattice through the upper air to probe chemistry. Each would look like an odd natural event unless we are paying attention. Each would be a kind of question. Do you see? Can you measure? How fast do you learn? And yes, there is a darker endpoint we cannot ignore. Conversation as prelude to control. In that path, a signal arrives not to greet, but to distract while other tools move. The defense against that is not paranoia, it is resilience. Hardened infrastructure, redundant timing, cross-check networks. The same posture that protects us from storms and cyber attacks protects us from clever probes. Preparedness is not aggression, it is just good engineering, so we watch the spectrum unfold. Silence would still be an answer. Curiosity without dialogue would still be an invitation to improve our instruments and our cooperation. Conversation would be the headline of centuries. The most important truth is that all three demand the same muscles: patience, rigor, honesty. If 3i Atlas chose to speak, we will hear it. If it chose to watch, we will learn to watch back. If it chose to leave, we will still have learned how to organize a planet around a question. A mystery becomes manageable when you draw its decision tree. We have one now. Over the next 4 months, geometry rolls like a conveyor belt. Each station offers a test. If the sky gives us X, we infer A. If it gives Y, we infer B. Not prophecy, just clean forks in the road. November brings the reappearance. December brings the distance minimum. Early spring brings the giant planet pass. Each check separates comet from craft a little more. Let us map the if-then, so when the frames land, you already know what they mean. If, as the glare fades in early November, a broad coma blossoms and 2 classic tails snap into place, then the natural script climbs fast, dust tail curving with the orbit. Ion tail, pointing cleanly away from the sun. That is textbook. Add a brightness surge that follows a smooth, heating and cooling curve, and you have the kettle whistling at last. If instead, the field stays oddly clean, with a tight, persistent core and only a thin puff where a fog should be, Then we keep the artificial page open and bend it at the corner. If tracking solves a tiny discrete change in the path centered on closest approach, the millimeters per second, that appeared like a single tap, then the propulsion hypothesis earns a star. Natural outgassing pushes look messy, correlated with visible venting and brightness hiccups. A surgical nudge at the one moment when physics multiplies your energy is strategy, not weather. If the orbit solutions glide through perihelion without a crisp kink, the machine case does not die, but it loses one of its favorite signatures. If new points of light separate in November along clean arcs, spreading by tens of thousands of kilometers with simple, predictable geometry, we are likely watching deployments. Debris makes smeared trains. Deployments make handwriting. The faster those points settle into resonant orbits, Earth-Moon parking spots, solar Lagrange points, quiet inclinations, the more they look like sentries, relays, or surveyors instead of shards. If no companions appear at all, or if a ragged string of fragments tumbles away, the needle swings back towards stress and fracture. December's approach to our distance minimum brings the listening tests. If narrowband radio lines rise at quiet frequencies where nature is stingy, and if they persist after correcting for Doppler shift across multiple dishes that share no hardware, call the alert. That does not mean we found neighbours. It means we found a signal that demands planetary attention. If the spectrum stays bare and the object acts like a stoic lamp, that silence is itself a message. A careful intelligence would not need to speak now. Silence can be strategy or indifference. We will note it and keep our ears open. Thermal and polarization will write their own if-then. If mid-infrared maps show a wide, warm blanket around the nucleus, and polarization curves match dusty grains across angles, then you are looking at coma physics in action. If infrared paints a narrow, very hot, sunward face, and polarization refuses the classic dust signature, then a hard surface or engineered skin stays in play. These are not subtle distinctions. A world full of modest telescopes can read them together. January and February are where patience pays. If the metal lines nickel, chromium track heating and cooling like clockwork, and if iron finally sings alongside them, chemistry returns to familiar ground. If nickel and chromium keep dominating while iron stays shy even after the hot pass, the alloy story steps out of the corner and into the center of the room. Add a spatial map that pins metals to a persistent sunward face, and the case grows ribs. March hands us the giant planet test. If the object and any companions wander near Jupiter's magnetic dominion, instruments already there can taste what they shed. A comet that still breathes leaves ions and dust for fields and particles sensors to measure. A machine that stays clean leaves little but gravity to report. Even a null result is loud here. A desert where a river should be is a sentence you can read from millions of kilometers away. Threaded through all of this is a social if-then. If institutions publish windows, negatives, and raw numbers, trust climbs and rumor withers. If teams hold data too tightly for too long, vacuum forms and stories rush in. The scientific method works even on YouTube time when the receipts appear quickly and the tests are pre-declared. We are not just measuring a sky object, we are measuring our ability to cooperate with ourselves. Now put it all together. If we see a classic bloom, messy fragments, iron lines waking, and no precise nudge at closest approach, the story closes as comet with unusual seasoning. If we see a stubbornly clean core, a surgical micro, burn, purposeful companions, metals that behave like parts not dust, and structured emissions in radio or light, then we are almost certainly looking at technology. If reality lands between, we keep walking the tree. Science is a game of narrowing, not one thunderclap. The comfort here is that we do not need faith. We need timing, discipline, and a few weeks of good weather across a planet. As the calendar turns, the forks will resolve, the ifs will become thens. And whether we file 3i Atlas under nature's weird cousin or under visitor, the map we just drew will have taught us how to read the next one faster. That is how a species grows up, by turning awe into checklists, and checklists into knowledge we can share. There is a reason this story has gripped so many people who do not usually care about spectroscopy or orbital mechanics. It is not just the maybe of aliens, it is the promise that we can act like a crew instead of a crowd. 3i Atlas is a mirror. It shows us how we handle mystery when the stakes feel personal and the clock is visible. Whether the object is a comet having a weird season, or a machine with a patient plan, the way we respond will teach us something about who we are as a scientific civilization. If it is natural, we still win. We will have mapped a chemical outlier from another star and tightened the models that explain how cold worlds form and shed. We will make better predictions the next time a visitor swings by. We will have built a standing global playbook that tells professionals and citizens how to coordinate light curves, polarization sweeps, and thermal maps without stepping on each other's toes. We will have learned how to ride out blind windows without feeding a rumor economy. That muscle will matter for every eclipse, every solar storm, and every deep space anomaly to come. If it is technological, the win is obvious and heavy. We will move from a century of listening for whispers to a decade of watching hardware. The question are, we alone will stop being a poem and start being an engineering problem. We will need protocols that are more than polite letters. We will need traffic rules for orbits we once thought were empty. We will need a shared ethic for how to study without provoking and how to communicate without grandstanding. That shift will be hard. It will also be exhilarating. History will not end. It will widen. Either way, the incentives finally point in the same direction. Open methods, published windows, fast release of raw numbers, respect between amateurs and institutions. When those habits take root, misinformation has less oxygen, and good ideas travel faster than fear. A high school club in Nairobi should be able to run a polarization sequence that matters. A university team in La Serena should be able to fold it into a global curve within a day. A retired engineer in Sapporo should be able to grab raw frames and test a claim without begging a gatekeeper. That is not utopia. It is workflow. There is a cultural dividend too. Big collective puzzles knit communities that do not usually share a table. Radio amateurs and particle physicists swap notes. Pilots and poets end up in the same live stream. Kids ask better questions because the adults are not faking certainty. Curiosity becomes a public act again. That matters in a century where attention is usually harvested, not cultivated. A planet that remembers how to wonder together is harder to fracture. We should be honest about the emotional load. Not knowing is hard. It tempts us to declare a winner early or to retreat into irony. The antidote is rhythm. Measure, publish, rest, repeat, build rituals that make patience visible. A weekly global bulletin that lists what was seen, what was not, and what that means next is more powerful than any single viral frame. It gives people a place to put their attention that is both exciting and sane. There is also a responsibility to teach. The words, Oberth, the effect should feel friendly now, not arcane. The idea that metals can glow in gas and tell stories should feel like kitchen physics, not wizardry. The difference between debris and deployment should be something a teenager can sketch with a pencil. When knowledge moves from arcane to ordinary, panic has fewer hiding places. We are not trying to turn everyone into an astronomer. We are trying to make the night sky less foreign than a trending tab. Policymakers have a part to play that does not require grand speeches. Fund small, agile sensors that can pivot quickly when a surprise appears. Support data archives that welcome public use instead of burying raw numbers under forms. Encourage agencies to pre-write their transparency rules for blind windows so announcements are automatic, not improvised under pressure. None of this is expensive compared to a single launch. All of it buys trust at a discount. Media can tune its instruments too. Curate uncertainty. Instead of pretending, every hour brings a twist. Highlight null results when they close real doors. Reward outlets that post receipts. When you must use dramatic language, pair it with the plain test that could collapse the drama tomorrow. That way, the audience learns to love the method, not just the cliffhanger. A world that is hooked on good process is a safer place to stage a big mystery. And then there is you. You are not an extra in this story. Your telescope might be in your backpack, in the form of a phone you can hold to an eyepiece. Your attention is a resource. Spend it where it multiplies the signal. Celebrate the observers who publish their misses, as well as their hits. Share the if-then map so your friends know what to look for and when to hold fire. The comments you write and the patience you practice are part of the culture we are trying to build. This is the part of the documentary where someone usually says everything will change. That is not quite right. Many things will remain beautifully ordinary. Sunlight will still climb the kitchen wall in the morning. Buses will still sigh at corners. The change is subtler and more durable. We will add a new reflex to our public life. Faced with an object we do not understand, we will think together before we shout. We will test together before we judge. We will keep our sense of wonder and our sense of proportion in the same frame. Soon, the curtain lifts. The sky will pick a branch on the map we drew, comet or craft or something we have not named yet. When that happens, remember how much of this was never about the answer. It was about the way we walk toward it. If we keep that stride, the next mystery will not catch us flat-footed. It will find us ready. This began with a paradox you could feel in your ribs. A body rushing toward the sun that looked like it should have a proud tail and instead offered a needle straight at the light, nickel humming while iron stayed shy. A path that hugged the planetary racetrack and hit its speed peak in the one spot we could not watch. Could this all be a cosmic coincidence? Or are we watching a plan unfold in plain sight? That is the question we have carried like a live wire through every chapter. Now we are at the threshold. The curtain starts to lift. The next images decide which story lives. Help us read them right. Here is the heartbeat of the whole film, slowed down so you can hear it. If a natural traveller gets cooked hard, it blooms. A bright coma swells. Dust writes a gentle curve. Ions draw a straight arrow away from the sun. The light stutters with vents and spin. Fragment trains appear when the nucleus falters. Chemistry relaxes into familiar ratios as heat takes command. That is the comet song. It has verses we know by heart. If that chorus hits as the glare fades, we will applaud, update our models for weird interstellar chemistry, and frame the odd months as a masterclass in planetary science. If a machine chose this path, it will rhyme with A, different music. Shape stays sharp. One face keeps taking the heat. Motion picks up a tiny surgical scar at closest approach, exactly when physics offers the biggest bargain. New points peel away along clean arcs and settle into quiet orbits that make geometric sense. Spectra keep favouring metals that sound like parts, not dust, while iron remains curiously late to the party. The radio sky either stays disciplined or speaks in math that anyone can test. That is posture, control, and intent. If the sky writes these lines, we will be looking at technology. We have drawn the if-then map so you do not have to guess. Coma and classic tales equal nature. Surgical kink and purposeful companions equal craft. Thermal blankets and dust polarization equal nature. A narrow hot plate and non-comet polarization equal craft. Nickel that moves with temperature and iron that wakes is nature. Nickel and chromium that ignore the thermostat while iron stays absent is craft. The beauty here is that none of this requires faith. It requires clocks, patience, and a planet that remembers how to do science in public. The blind window, the rumour mill, and the temptation to fill silence with stories are part of this test. We pass that test by telling time out loud. We pass by, posting the observing windows, the negatives, the raw curves, and the honest maybes, as quickly as we can without breaking instruments or people. We pass by asking amateurs and professionals to behave like a single distributed sensor instead of a scrum. We pass by building the muscle that turns awe into checklists and checklists into knowledge. That muscle will matter again, whether the next surprise is a visitor, a storm, or a whisper from a world we have not named yet. There is a cultural wager sitting under the chemistry. The wager says, a world can think together before it shouts. It says curiosity can be louder than panic. It says teenagers can learn words like Oberth effect and feel ownership rather than exclusion. It says patience can trend. That is not a soft dream. It is hardware for a century that will throw bigger puzzles at us than this one. If 3i Atlas turns out to be rock and ice with a strange recipe, the wager still pays. If it turns out to be engineered, the wager becomes the first chapter of how we choose to live with neighbours. So, here is what happens next, in human words. The glare eases. Observers on 3 continents grab spectra and heat maps. Backyard rigs run polarization sets and time series. Survey cameras check the field for companions. Deep spacecraft taste the plasma lanes. Radio dishes listen where nature is quiet. The first results arrive. We stack them against the if-then map. We do not force a verdict. We let the pattern emerge across days rather than minutes. When a fork locks in, you will feel it, because the evidence will rhyme from tool to tool. And here is where you come in, not as an audience, as crew. Subscribe so you do not miss the recovery windows and the live data links. Hit the like so the algorithm pushes this plan to the people who can use it. Tell us in the comments where you are watching from and what time it is there so we can knit a coverage map that does not sleep. Share this episode to X, to Facebook, to Reddit, and into the group chats where observers plan their nights. If you run a telescope, grab the polarization guide and the cadence we posted in the description and add your slice. If you do not, be the person who asks for receipts instead of rumours and makes patients feel normal. We will keep our end of the bargain. We will publish the windows. We will post null results with pride. We will show raw numbers when it is safe. We will flag real forks the moment they lock. We will correct quickly when they do not. We will give you the rulers so you can check us. That is how trust works when the stakes are this high and the subject is this strange. Soon, the sky speaks. It will not be shy. Either the kettle sings, or the instrument holds its note. Either fragments smear, or companions write clean handwriting across the dark. Either iron wakes, or metals keep whispering the language of parts. Either the radio band stays hushed, or it clicks into math. Whatever arrives, it will give us the answer we earned with discipline, not the answer we begged for with fear. We end where we began. A body rushing toward the sun that should carry a tail, and might not. 8 days hidden at the very moment when the physics turns to gold. A world that could choose to behave like a crew. Stay with us through the reveal. Bring your questions and your rigor. Then carry that habit into every mystery that follows. Like, subscribe, and share, so the net is as wide as it can be. The curtain is lifting. Let us meet whatever walks out with clear eyes, steady hands, and the best version of ourselves.